Hello, my name is Oliver, and today I'm going to talk about derandomization from time-space trade-offs. So in this work, we're going to be concerned with Fnp search problems. So just to recap the definition of these are search problems defined by relations, binary relations relating strings representing instances to a problem with strings representing potential solutions. And we say xy is in this relation if y is a valid solution to the instance x. And the relevant properties are that this membership of basically testing of a solution solves an instance should be testable in polynomial time. And there should be some upper bound on the length, polynomial upper bound on the length of solutions in terms of the length of instances. And the relevant sort of computational task associated with these is given x, find a y such that y solves x, or else determine that there's no solution. Now, the subclass of FNP, known as TFNP, are the problems for which, relations are for which the following theorem holds. The theorem states, for all x, there exists a y such that xy is in the relation. In other words, for every instance to this problem, there is always a solution. And the reason I phrase it in terms of the truth of this associated theorem, which I'm calling phi sub r, is that sort of one of the main reasons for studying TFNP is that studying the complexity of the total search problem R is sort of a surrogate way of understanding the constructivity of the theorem phi sub r stating the totality of this principle. So in particular, if a theorem is sort of inherently non-constructive, one way to sort of explain or justify what that means is that there's no efficient way where, given an x, we find this y which is guaranteed to exist by this theorem. So typically in complexity, or in general, when we say something is non-constructive, this is sort of seems like a purely negative result. But in this work, we're going to argue that this can actually be very useful, even computationally. And so this perspective sort of originates in cryptography, where sort of an insight that was sort of first stated by Yao in his paper on trapdoor functions, that sort of non-constructive theorems can have effective counterexamples which let us bypass information theoretic barriers. So what do I mean by this? Well, sort of maybe the most important example of this is a non-constructive theorem by Shannon on information theory, which in particular implies that, so the source coding theorem, which implies that for any deterministic function x applied to a random variable, f applied to a random variable x, f cannot increase the entropy of that variable. So the output of f has at most the same entropy as the input. And what Yao noticed is that even if this theorem is of course true and was proven by Shannon, his sort of argument doesn't give us an efficient way to sort of witness the truth of this theorem. And in particular, there are some efficiently computable functions, which we now call pseudorandom generators, that take a small input and stretch it to a much bigger one. But somehow the output of these functions appears to have like the full amount of randomness as its output length could have. So in particular, it stretches n to n plus 1. Shannon's theorem tells us that the output has entropy at most n. But for many natural, efficiently computable functions, it seems like the output appears to any efficient observer to have entropy n plus 1. And so in some sense, these PRGs are like an effective counterexample to these impossibility theorems of Shannon. And in particular, in the realm of cryptography, this sort of lets us bypass information theoretic barriers and perform interesting tasks which like information theory would tell us that we can't do. And so in this work, we're going to use sort of non-constructivity. Instead of giving some advantage in like an information theoretic or secret sharing type of task, we're going to get a computational advantage for solving a particular problem. And so in particular, we're going to say that if a certain pigeonhole principle is inherently non-constructive, I'll explain what that means in a moment, this is going to imply a computational advantage where we can simulate any RAM computation using a very small amount of space and with almost no overhead in time. So perhaps like the most interesting way to look at this is by contrapositive, where we're going to be able to show that if we assume a uniform lower bound, in particular a time-space trade-off, this is going to imply the constructivity of a certain pigeonhole principle, which in particular we can view as sort of a derandomization of a natural search problem in TFNP. So the problem that we're going to look at is what we can call the bijective weak pigeonhole principle. And this principle tells us that if we have a function from n bits down to n minus 1, we'll think of this as like a compressing function that compresses n bits down by 1 bit. and then we have a decompression that goes from n minus 1 back to n, then this cannot be like a lossless compression scheme. There must be some input x such that when we feed it through these two maps, we get back a different string. So this string that we're looking for is somehow incompressible by this compression scheme. And instead of looking at this, so one way to view this problem is as a classic TFNP search problem where we're given the circuits, the function C and D specified by circuits. But what we're going to look at today is sort of a uniform instances of this problem. So scenarios where these maps C and D are defined for all n by a single pair of polynomial time Turing machines. And so what our main theorem is going to show is that if there is an effective counterexample to the Pigeonhole principle, so what I mean is a uniform instance C and D such that no polynomial time algorithm can find those n-bit strings which are incompressible for this scheme, then there's going to be a universal simulation of RAM computations in small space and nearly linear time. So again, looking at this in the contrapositive, or just stating this in more explicit terms, we're going to have that one of the following two claims is true. The first is that for every pair of polynomial time Turing machines C and D, such that C decreases its argument by 1 bit and D increases, there is a polynomial in n algorithm that constructs an n-bit string which is incompressible for this pair. So that's the first statement. And the second statement is that for sufficiently large t, time bounds t, every t time RAM computation can be simulated in t to the 1 plus epsilon time and t to the epsilon space on a one-tape Turing machine. So what we get is either there is a constructive witnessing algorithm for the Pigeonhole principle, or there is a universal simulation of RAM with low space and little overhead in time. And so why do I call this a derandomization problem? Well, let's just look back at the definition of this Pigeonhole principle. We see that with probability 1/2, if I sample an n-bit string at random, it's not going to map back to itself because sort of the domain is twice as large as the codomain of C. And so in particular, there's a natural randomized algorithm that just samples an n-bit string and tests whether it's a solution. And what we're wondering is, can we de-randomize this and get a deterministic one, at least when in the case where C and D are given by uniform Turing machines. And so I'll now jump into the proof of this. So the setup is we're going to fix some positive epsilon greater than 0, thinking of it as being like very, very, very small number. And we're going to let M be an arbitrary random access machine that runs in time t. So for starters, we're going to set some parameter w to be t to the epsilon, and we're going to focus on our supposed compression scheme C and D fixed to length w. So I guess backing up a little bit, the way this is going to work is we're going to say, imagine we have some compression scheme C and D such that no polynomial time algorithm ever finds an incompressible string for this pair. That's going to give us a way to simulate this machine M in low space t to the epsilon and time t to the 1 plus epsilon. So, as I said before, we're setting this value w to t to the epsilon, and we're going to focus on this compression scheme C and D when we fix the input lengths to be w, this t to the epsilon value. And in particular, we're going to make the assumption that this compression scheme C and D, instead of changing the bit length by 1, it does it by a factor of 2. In the paper, we show this is without loss of generality, but it's easier to work with this for now. So C takes 2 w-bit strings and compresses down to w, and D takes w and extends out to 2w. And by our assumption, we're sort of imagining that C and D are a counterexample to the Pigeonhole principle. So no efficient observer is going to be able to find the input where this scheme fails to compress a string of length 2w. And we're going to use that to our advantage to build a data structure which lets us simulate our machine M in very low space and time efficiently. So the setup we're going to do is we're going to take our decompressing map, which extends from w bits to 2w, and we're going to apply it in like a tree-like fashion for k levels. So we have D, the first level of D maps w to 2 w-bit strings, and then we feed each of those into D again, and we get 4w, and we continue k times till we get 2 to the k w bits at the top. And the parameters we're going to set is we're going to have log t be the depth of this construction, so the number of leaves at the top is t. And now, sort of, what are we going to do with this tree construction? Well, for any possible w-bit input y, I'm going to call this the seed. And what I can imagine doing is feeding it through the bottom and sort of letting its value percolate out to all of these leaves. And at the end, I get sort of t different values at the top of these leaves. And what I'm going to imagine is that this represents sort of a t-bit memory Really, it's t times w, but we can just treat each leaf as like we only care about storing, let's say, either the all 0 string or the all 1 string. So we have these t sort of memory locations, and y is going to function as a compressed representation of this memory. So in particular, y has t to the epsilon bits, but it's sort of representing a memory, which is at the leaves, of length t. And now sort of what we're going to do is we're going to use this virtual memory to simulate the random access memory. And we need to sort of three main operations to work. So first, we need to be able to initialize the value of the memory to 0. We need to be able to access a particular bit of the memory. And we need to be able to update each bit of the memory to a desired new value. And this is what a random access memory, the only things that it does. If we can simulate all of these in sort of t to the 1 plus epsilon time and t to the epsilon space, then we'll be able to get through with the whole simulation. So we'll start with the initialize operation. And the idea is, so far we've only been looking at our decompressor map, which is extending the number of bits. But now we're going to look at the compressor. And what we're going to do is we're going to take two strings, like 0 to the w, 0 to the w, w bits long of zeros. And we're going to run them through the compressor and get some output x1. And then we're going to take two copies of x1, run it through again and get x2, do that with x2 to x3, and do this k times, like for the where k is the depth of the tree. And the result, so assuming that we're never finding an incompressible string for this compression scheme, in other words, assuming that we never find a witness to the Pigeonhole principle, then when we feed x3 back through D, we should get whatever we put into C. So we should get 2 copies of x2. And then if we feed those through D again, we should get 4 copies of x1. And finally, we feed those through again, we should get all zeros at the top. So the point is we set, like assuming we never found a witness to the Pigeonhole principle, we set all the values of all these leaves to 0. And the time we spent is only proportional to the depth, which is log t, times the time it took to evaluate C and D, which we assume is polynomial in their input length, so poly t to the epsilon. So overall, this is t to the O of epsilon. Now, for the access, so the next thing we need to do is be able to access a particular leaf of the memory. To do this is very simple. So memory positions are indexed by paths in this tree of length log t. And to index, to get the particular value, we take the seed and we just run it through the tree, sort of only keeping track of the values along this path to the leaf. And this is, again, log t different evaluations of the functions, which each take t to the O of epsilon time. So again, this is t to the O of epsilon for each access. And so the final step then is this update procedure. What the update is we want to set a certain position, a certain cell of the memory, to a new value. So the way that we do this is, so on the left here, you can see we sort of start by running this seed through the tree along the path to the position we want to access. This is exactly what we would do just when we're accessing a memory. But the new thing we're doing here is we're also going to keep track of these off-branch values we get. So when I ran y through first, I want to go right to get to the memory that I want, but I'm also going to keep track of like whatever this value was here. And then I do the same thing here and finally here. And now, sort of the second step, we're going to work backwards. So what I want to do is I want to change this value x to some new value s. And now I'm going to take s and z1, and I'm going to run them through my compressor and get out some new value v1 here. Now I take v1 and the off-branch value here, compress them again through here, and finally z3 and v3 over here, and compress them to our new seed here. And now the idea is, if I run this new seed through the tree, by assumption that all of these, that I never witnessed the Pigeonhole principle, so all of these compressions worked, when I feed it through here, I should get, like along this path, I should get to this new value s. But if I go anywhere else in the tree, then I reach one of these off-branch values, which I kept the same as whatever it was before. So this immediately implies that the value of everything in this sort of subtree rooted at the first position that I branch off is going to be exactly what it was before. So I maintain all the other cells of the memory that I didn't want to change, and I change just the value that I wanted to. And again, this is all functioning in time proportional only to the depth of this construction, so depth log t times the evaluation of C and D, which is t to the O of epsilon. So, as a recap, what did we just do? So we imagined that we have some counterexample to the Pigeonhole principle, so a pair C and D defining some compression scheme, such that no efficient algorithm could witness the strings that it fails to compress. What we did with that is we simulated an arbitrary t-time computation using this virtual RAM data structure. And now we proved that all the operations in this data structure run in time t to the O of epsilon and space t to the O of epsilon, and they faithfully maintain the memory of our computation, assuming that the Pigeonhole principle fails for these maps. So what I mean is anyone who could spot a failure of this low space simulation could, from that failure, find a witness to the Pigeonhole principle for C and D. So if we assume that no efficient algorithm can witness the Pigeonhole principle, then this means that the simulation must work and we faithfully maintain the state of the memory at all steps. So taking epsilon to 0 in this construction, so all of the bounds before were of the form like t to the O of epsilon, t to the 1 plus O of epsilon, but as we take epsilon down to 0, we just can eliminate the O for arbitrarily small epsilon. And now the contrapositive, maybe the most interesting thing, is we get that if this simulation fails, then we witness the Pigeonhole principle for C and D. In other words, locate an x such that d of c of x is not equal to x. And so what that means is if we assume a time-space trade-off that you cannot simulate a time t computation in t to the epsilon space and t to the 1 plus epsilon time, then this implies that there is a deterministic algorithm to witness the Pigeonhole principle. In other words, a derandomization of the natural algorithm for the bijective weak Pigeonhole principle. So now that I've stated all of that, I guess the next interesting thing we want to know is like, what are these uniform instances of the Pigeonhole principle that we might care about? And unfortunately, I can't show you one where both sort of the maps C and D are unconditionally polynomial time computable and the uncompressible strings are somehow interesting a priori. But what we do know is several examples where either the compressor or the decompressor is computable with an oracle for some interesting non-NP complete problem. And the incompressible strings are sort of interesting explicit construction tasks. So the first such example is going to follow from some work in bounded arithmetic by Paris, Wilkie, and Woods. And what we can show using their techniques is that there's an efficiently computable compression scheme with an oracle for factoring. So like here, this map is going to be the compressor C. This is the compressor D. Both of these are polynomial time computable with a factoring oracle. And the incompressible strings for this pair, so the solutions to the Pigeonhole principle for this pair, are going to be large prime numbers, so like 32 n-bit primes of magnitude greater than 2 to the n. And so it's a like notorious open problem how to efficiently deterministically construct prime numbers that are large. And it's even an open problem with a factoring oracle. And so that's going to be our first example, and we'll come back to like how our results imply something about this problem. And the other interesting example are about hard truth tables for functions. So here, the sort of natural uniform instance of the Pigeonhole principle we can look at is the map that takes a big n-bit string, which we can think of as like a power of little n, like power of 2, like 2 to the little n. And we interpret this as the truth table of a Boolean function on little n bits. And what we do is with an oracle for circuit minimization, we map it down to a description of a small circuit on like that takes fewer bits to describe, which computes that truth table. And then the decompressor like can evaluate that truth table and map it back to the original representation as a raw truth table. And so the idea is the solutions to this uniform instance of the Pigeonhole principle are the hard truth tables of high circuit complexity. And sort of the complexity of computing this compression scheme is like polynomial time with an oracle for circuit synthesis, which again is not known to be an NP-complete problem. And so sort of with these examples in mind, what we get is that assuming time-space trade-offs of the kind I mentioned before, we get that efficient compression implies efficient construction of incompressible strings. So what do I mean by that? Let's apply that to each of those two examples. On the one hand, so both of these 1 and 2 points are assuming time-space trade-offs. We get that an efficient factoring algorithm implies an efficient large prime construction algorithm. And for the second one, we get that an efficient circuit synthesis algorithm, so an algorithm that finds small circuits for a truth table or tells you that none exist, implies a hard truth table construction, so circuit lower bounds for E. So that's sort of the results we can get for these specific uniform compression schemes. So if we sort of, one unfortunate thing about the statement of this theorem is it's like assuming this one thing which we can't prove, we get an implication between this and that where maybe these efficient compression algorithms, we already don't believe that they exist. So if we want to get sort of a more straightforward implication, assuming something we believe, we get something else which we want to prove. we can get that if we move over to non-deterministic time-space trade-offs. So what I mean here is instead of looking at deterministic machines like before, we're just going to look at non-deterministic t-time machines. And the time-space trade-off assumption is that a t-time non-deterministic machine cannot be simulated on a one-tape non-deterministic machine that uses at most t to the epsilon space, t to the epsilon non-deterministic guesses, and only t to the 1 plus epsilon time. So this is like sort of the natural analogy of the deterministic time-space trade-off assumption, but in the non-deterministic machine case. And this one's actually even more sort of believable because not only are we restricting the space, but we also restrict the number of non-deterministic guesses. So I think, here is a pretty natural time-space trade-off assumption for non-deterministic machines. And using these same techniques, similar techniques and some extensions, which I won't show here, we can get from this that like a concrete circuit lower bound, which is that e to the np does not have circuits of size, like basically requires the maximum possible circuit complexity, 2 to the n over 2n. So, yes, from assuming these things for non-deterministic machines, we can get like an unconditional circuit lower bound from that time-space trade-off. And sort of these hardness, we can think of this as sort of a hardness randomness connection, or like a basically assuming some lower bound, we get a de-randomized construction of some combinatorial object. But unlike previous hardness randomness trade-offs, the sort of lower bound assumption we're making is completely uniform. So we're only assuming the hardness of simulating t-time machines for other uniform machines that run in some restriction of resources. So in this case, space and non-deterministic guesses. In the other case, it was just space. And so sort of a natural question, so that's sort of the end of the main results of this that I'll present here. And the natural question that arises from this, I think, is there a way to get more of these sort of unlikely simulations from effective counterexamples to other principles? So what I mean by this is, can we look at some other TFNP principle, like the Pigeonhole Principle, but a different one, and sort of find a way to show that if we had an effective counterexample to this, we could get some unlikely simulation of general machines with a restriction in some resource or another. And sort of maybe one caveat, a reason that this might not work is perhaps that this phenomenon is like really unique to problems that are amenable to the de-randomization. So as I mentioned, the Pigeonhole Principle has a randomized algorithm, and perhaps that is sort of the key property that makes this sort of simulation argument work. But I think it would be really interesting to find other examples where this phenomenon occurs. Yes, so that's the end of my talk. Thank you for listening.